All right, in this last example, we're given that f of 2 is 3 and f prime, right, the derivative at 2 is a negative 2. And it asks us to find the coordinates of the points A, B, and C. All right, so this red line is the tangent line to the function f of x. And we know that the derivative at 2 is the slope of that tangent line, right? It looks like this tangent line is touching the point right at x equals 2. So essentially we can, well, first of all, let's start with point A. Point A is just this point right here. This point right here, this point is the point 2, 3, right? The x value is 2, the y value is 3, which is the value of the function. So this point right here is 2, 3. All right. Now, the other 2 points are on the tangent line. So if we have an equation for the tangent line, then we can find these other points. And we can find the equation of the tangent line because we have a point, right? We have a point that is on the line. It's on the graph of f of x as well, but it's also on the tangent line. And we have the slope, right? This right here is the slope. This is the slope of the tangent line. The slope is equal to negative 2. And if we have a point and a slope, we can write the equation for a line, right? So the equation, the point slope formula for the equation of a line is y minus y1, where that's our fixed point. M is our slope, and x minus x1, where x1 is the fixed point. All right, so our fixed point is 2, 3, and our slope is negative 2. So let's put those values in. We get y minus 3 is equal to negative 2 times x minus 2. Okay, now that's the equation for a line right there, but usually it's nicer to see it in the slope-intercept form instead of the point-slope formula. This is the point-slope formula. The slope-intercept form of a line is y equals mx plus b. So let's rearrange this and make this a function for y in terms of x. So I'm going to distribute the negative 2, right? Just distribute this across. So I'm going to get plus 4 when I take negative 2 times negative 2. And then I'm going to add 3 to both sides. All right, so let's rewrite this. Let's clean it up and combine those constants. We get negative 2x plus 7. Okay, so that's the equation for the line. All right, now the points B and C are on that line. So all we need to do is take the x value and calculate the y value. All right, so let's first of all, this is point B. This is at x equals 1.5. Right, so we have the equation for the line. So then our y value is just going to be negative 2 times 1.5 and then plus 7. Okay, so the y value looks like it's going to be a negative 3, right? 2 times negative, or negative 2 times 1.5. So that's a negative 3 plus 7 gives us 4. All right, so point B is going to be, let me write it up here. Point B is going to be 1.5, 4. Okay, that's what that point is. So point C. Point C is at x equals 2.5, right? 2.5. And so all we need to do is put that x value in to our equation for the line. Okay, so we get negative 2 times 2.5, that's a negative 5, and add 7, we have 2. All right, so point C down here is the point, this is going to be, what, 2.5, let's see, where should I write it? 2.5, 2. That's what point C is. All right, so let's write it down here. Let's summarize what we got here. We got point B is 1.5, 4. And point C is 2.5, 2. All right. So now we're kind of getting ahead of ourselves. We're going to be doing more with derivatives, but one of the things that is useful about the tangent line is that you can see near the point A, the values of the function f of x and the values of the tangent line are fairly close. So oftentimes we use the tangent line to approximate a function, right? So we can approximate the values of f of x near A with the tangent line. And so the tangent line will become an important thing to use. So that's all I have for this section, and I'll see you in class.